So is my screen visible?
Yes, ma'am.
This was the introduction. So I have seen that many of you have given the codes and all that. I'll check it and I'll inform you. And I haven't got the examples of back learning yet. Okay. Am I audible first?
Yes, ma'am.
And Ashi, I have to reply you. I checked your message. I forgot. Now only after seeing your name, I like recalled that you have messaged me. I'll reply after the class only.
Sure, ma'am.
Suboptimal thing. I was also thinking that suboptimal will have more frequency, but then I also okay. I'll reply in detail about that thing. We'll take an example and then.
Ma'am, I also wanted to ask one more doubt from week 4.
Hmm.
I wanted to ask, ma'am, is there a difference between like MDPs with deterministic rewards? Like, what do they mean by deterministic rewards in MDP?
Okay.
Don't the
Mhm.
rewards depend on a probability distribution in MDPs?
Yes, they do depend on probability distribution. Okay, let's start it. I'll cover this topic. Don't worry. Many of the doubts are in the Slack as well. We'll study that only today, the week 4 session only. So we'll cover these all the things. Then we'll come to your question as well.
Okay, thank you, ma'am.
So till last class, everything is clear.
Yes, ma'am.
Today I only 3, okay, 5 students have joined. Okay, let's start. What do you mean by long-term rewards?
Which consider not just the current state, but the future states as well.
Example?
Total return.
Okay,
Total expected.
total expected return, that I got it. In the technical term, in our daily life, an example of long-term reward.
Ma'am, when we are doing cycling, so we don't focus that whether there is one goal that we have to keep balance, but there is also a long-term kind of negative reward. Like if we crash the by the cycle, like maybe we stepped over a stone, and then we'll get the long-term reward as negative.
Yes, yes. As she said that if we are cycling and suppose there is a stone and we lose our balance, but at that moment only we'll not fall down. It may be the probability that after some time we might fall down. So that is a long-term chase, as said by Gitika, studying for exams. You all are correct. So now coming to returns. What is return? What I have written?
The total return that we expect after we take the action in the current state, like including that. So the reward that we potential reward, basically the potential reward we'll get in the long run.
Yes, you are correct. That potential reward we get in the long run. That is basically the return here. So, T here we are thinking as finite, first thing. So, one more thing I want to ask. So, is T a random variable or it is deterministic?
Random variable.
Why?
Because it can vary from experiment to experiment.
Can you give an example?
Chess is a good example. You don't know how many moves it will take until you win.
Yes, you are correct. That t is a random variable. We don't know when we'll end, as given by him an example about the chess. We don't know when we lose or when we end, how many moves are remaining there. So basically, t is a random variable. And the total return is basically the sum of the rewards here. So basically, if suppose what they are saying is, if suppose that RT plus 1 and RT plus 2, I am ending in not a good ST basically. What is happening? I'm in the state S, I'm taking the action and the reward is there. Suppose I'm not like ST plus 2 is not a good one, but when I'll sum up all of them, then it may be that I'll get the max, like the whole of the sum will be the maximum one because I'm adding it up. Basically, that is the intuition behind it. Now, coming to t, t is finite. We are assuming t is suppose a random variable, actually a random variable, because it may stop at different times. Basically, like an example of chess, or I can say an example of tic-tac-toe also. Suppose t is infinite. Then what to do?
And we'll try to maximize the instantaneous reward that we get.
Okay. So, what is the approach here?
You can have a gamma.
Yeah. What is gamma?
So gamma is a weighting parameter which the rewards get progressively smaller with time.
Yes, you are right. Basically, discounted reward, I can say, or discounted return here. What is the other advantage of like having a gamma? One advantage is because it is infinite, and the other advantage you said, what is that?
And the sum will be bounded.
Some will be counted, and the other one.
More preference to recent rewards, like immediate rewards.
So basically, it is inspired by the psychology only that we will give more preference to the recent rewards rather than the far away rewards. Or I can say near-sighted rewards are more valuable than the far-sighted reward. That is basically the more like I can say the motive behind this gamma here, discounted reward here. And how we are saying that it is basically reducing that problem of infinity here. How this gamma is playing the role here? Can you explain me in detail?
Gamma is basically less than 1, right? So what happens is as we increase the power of gamma, so the terms become smaller and smaller, and eventually they tend to 0 as it tends to infinity. So we get an infinite GP sort of thing.
Yes, you are correct. Basically, gamma is less than 1, and this sum will like converts to something finite, or we are saying that we are like doing square then cube, and as we go forward, the sum will basically not explode, or that infinity thing will be like that will be overcome here. And the other thing is that what is here that is more valuable than what is here that is more valuable than what is at the last. Near-sighted is given the more preference in the far-sighted here. Can I say that gamma is playing a role that whether to give the preference to near-sighted or whether to give the preference to the far-sighted rewards?
Yes, ma'am.
Can someone explain me this?
And if gamma is 0, then we'll just consider the current reward. So it will be very nearsighted. And if we consider gamma as 1, then we are giving equal weightage to the current reward as well as the future reward. So it will be very far-sighted.
You're correct. So basically, we are having an option that whether you have to choose the collect the smaller reward immediately, or we have to wait to collect the larger reward afterwards. Whether we have to see the far-sighted view or we have to see the near-sighted view. Basically, if it is close to zero, then we can say that it is near-sighted. We are only focusing on the immediate one, and if it is close to one, then the far-sighted one. What is the other approach? One is the discounted rewards, returns, I can say, or discounted rewards. What is the other approach?
Just taking the average, I think.
Yes, yes. So just taking an average. You can say average reward return.
Ma'am, that is equivalent to gamma equals to 1, right?
Yes. We are taking the average and summing it up. Obviously, we are not taking gamma. It means that gamma is equal to 1. Okay. Then, okay, if what are the example or the systems where limit doesn't exist? What we are saying, if limit n tends to infinity, then we are taking this basically to this is infinite. To overcome this, we are saying that limit n. What if limit doesn't exist? What are the systems where limit doesn't exist? For examples. Yes, come on. I think this is.
When the rewards are very large, like if the rewards are very large, kind of so that
What is limit, first of all?
Limit is number of states. So when we have a lot of states, so like if we are playing, the agent is playing Subway Surfers game, so it can go for infinite time, like very long time.
If the what you're saying, can you repeat? If
There's a game Subway Surfers, so if the number of states is very large, like our experiment is going on for a very huge long period of time.
So you think if it is for a long period of time, then limit will not exist? Is
And
it
yeah,
If RT is unbounded,
artist? If I'm saying that it is bounded,
then the limit may exist.
Ma'am, there has to be a pattern, a periodic,
yes, periodic function.
yes, ma'am. This has to be a periodic function for limit to exist. Otherwise, we
It
cannot.
doesn't exist.
Yeah.
If periodic function is there, then limit doesn't exist. I think this is told in the class. So what do you mean by periodic function? Think for 2 minutes, like why limit doesn't exist for periodic function. What is limit? Value. We are saying that the function approaches, like value that the function approaches as the input is approaching a certain point, basically. So we limit n is 10 to infinity, which itself is meaning that it is very large. We are saying it is 10 to infinity, where like it is coming to some point where limit doesn't exist. I'm saying periodic function. Now tell me why limit doesn't exist in periodic function.
Ma'am, for limit to exist at infinite, it has to be a kind of asymptote. If the function is periodic, then even at infinite, the function's value can vary. It's not converging to a particular value. That's why we can't define the limit.
Yes, you are absolutely correct. It is not converging to a certain point, I can say. In periodic function, I can say what a periodic function, first of all.
Sin x. Yeah.
Sin x is an example. What is a periodic function? It keeps oscillating. Yes, you're right, Ashi. that the functions which are keep oscillating, or I can say the function which is repeating itself at regular interval.
Yes, ma'am.
F of x equal to f of x plus t.
Can you all write the example in the chat? Sin x, cos x, you are correct. So basically periodic f of x is equal to f of x plus t. Okay.
Yes, ma'am. Capital T is the time period then.
So how it is oscillating, how it is a periodic function?
I mean, we can parameterize x with respect to capital T. And by
Okay.
that virtue, it will be, ma'am, periodic function. I mean, every sinusoidal wave, apart from that, any wave function is periodic in nature.
Which is repeating itself, or I can say which is oscillating.
Yes, ma'am.
So what is the alternative for that?
There is, there is no repetition of pattern after a certain interval. The function.
What is that called? What is that limit called?
I mean, ma'am, I'm not getting your question. Can you?
What is the alternative if I have this periodic function, or I can say the example you gave where the limit doesn't exist, then what we can do?
So we sum it over the periods, I think. I mean, number of periods we are encountering, and then we can sum up, take an average.
Yes, yes. That what is that called basically? You are absolutely correct. We are basically taking the periods and then we are taking the average of them. What is that called?
Episodes.
Yes.
Like different episodes.
That is called average expected value.
No, something limit. It's called Cesaro limit. Am I correct?
Yes, ma'am. It was mentioned in the video. I forgot. Yeah.
Okay, let's take an example how the Cesaro limit is helping us if the function is periodic. Suppose, first of all, is this function a periodic one?
Yes.
No,
Why no? Why yes?
because at n.
Yes, because as n increases, it will become positive and then negative.
Okay.
Not exactly periodic, but yes, band.
N is equal to 1 now. Wait a second.
Ma'am, if we eliminate the n from the denominator, then it would be periodic. If n stays there, then it wouldn't be periodic, I think.
Yeah,
Yes,
it is a
it's
convergence,
actually
but not periodic.
oscillating.
Okay, let's take an example.
So oscillating is not enough to say that the function is periodic. It has to be equal. The values have to be equal at equal time periods. So
Yeah,
the function could be oscillating but non-periodic.
you can take the graph of damped oscillation. I mean, it was in the wave in class 11, 12. The damped oscillation is still an oscillation, but it's not periodic as the amplitude is decreasing as time increases.
Yes, you are correct that there are some examples when the oscillation is there and it is not periodic. Okay, can I say that if the value is repeating itself at a regular interval, then it is periodic?
Yes.
Something wrong is there. Wait a second. It is not coming as periodic, na?
Ma'am, it is
No, ma'am.
damping, like it is oscillating around 0, but the magnitude is getting decreased.
No, madam, there is no way it is periodic because it is divided by n. So it is going to converge, but not periodic.
Ma'am, to be very frank, this is actually the equation of a damped oscillation. If we
Yes.
plot, yeah,
Yes.
the amplitude is getting decreased.
Yes. 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 Can be related with Cauchy sequence.
Mm,
Yes, ma'am.
What is Cauchy sequence? Though I haven't taught it, but still.
The
From
difference
here, the
between consecutive
elements-
terms gets smaller.
Yes. So is it getting smaller?
Looks like it.
yes, ma'am.
Is it getting smaller?
Ma'am, no, if the sign wasn't changing, then it would be.
Then it could be, yes, yes. Okay, I'll come with some example of Cesaro limit. I was thinking, now is it periodic?
Yes,
Yes,
ma'am.
ma'am.
With a time period of 1.
Okay.
I think 2. I mean, a total cycle.
Yes, n is equal to suppose 2. Then, no.
Ma'am, from n equals to 0, it's 1. From n equals to 1, it's -1. And from n equals to 2, it's 1 again.
-1 to the power of 2n is periodic. 2n. -1 to the power of 2n.
-1 to power n is also periodic.
Yeah, this is also periodic.
This
Yes,
is also
it's
periodic, but if we had 2n, then it would have only the positive value. Negative value, it wouldn't have.
Then it is not periodic.
Yes, ma'am. It's a constant curve. It's a constant.
Power n is basically periodic, I can say.
Yes.
Yes, Kritika, you are right. It will be constant. -1 to power 2n. So let's try at least. Wait a second. Let's try this. So Cesaro limit is basically we are taking the average here of the periods. So let us try. The first is basically -1 to the power 1. Let's try from 1 only. And then minus power 2, that is -1 plus 1 by 2 is equal to 0. C3 is basically -1 by 3. C4 again 0. C5 is equal to 1 by 5. So we can say that it will converge to 0 after some time. Am I correct now? Is Cesaro limit helping us to converge? Though they are oscillating again, like they are coming to 0, but still they are reducing basically, and one time they'll converge to 0 after that. Am I correct?
Yes, ma'am.
So is it a right example of Cesaro limit? Is Cesaro limit helping us to for the systems, for the periodic systems?
No, ma'am. Here it's eventually converging to 0 as n is increasing.
So what is periodic? They are not converging to anything. The limit doesn't exist. But Cesaro limit, I can say that it is converging. So limit can exist here.
Yeah.
It is overcoming the system, periodic system, like the limitation of that.
Yes. Yes, ma'am.
Clear? Can I move forward? Everyone?
Can you explain what is Cesaro's limit once again, because I got disconnected.
Okay. Cesaro limit is nothing. I took an example like as told by everyone, -1 power n. It is periodic. Do you agree?
Yes, ma'am.
So what I did, that C1 -1 power 1 is equal to -1. Then what is -1 power 2? That is also -1. Then I took the average of both of them. -1 plus 1 by 2. That is 0 here. Now C3 is -1 power 3. That is 1. And took the average of these both. 1 -1 here, sorry. -1.
Okay, ma'am. I've got it now. Thank you.
So, ma'am, for Cesaro's limit to be applicable, I mean, there should be a kind of converging factor. The amplitude must be decreasing to a particular point.
Can you give me an example where it is periodic and Cesaro limit will like it will not exist? Like, yes, there are examples. You are correct that everywhere we can't apply the Cesaro limit. Yes, there is some alternative way in some places like this periodic function minus 1 power n. We are applying this and it is overcoming that periodic thing. Can you give me an example?
Yes, ma'am. For sin x, we can't apply Cesaro's limit.
No, you can. Tan you cannot.
Yeah, for tan also, I think. I mean, for tan, n tends to infinity, tan.
Let us take it as a homework assignment. Please write in the Slack in general only how like Cesaro's limit cannot be applied with like sin x, tan x, or some periodic functions and why.
Okay, ma'am.
And give me that also pack learning examples. Last class, then only I'll proceed with that.
Oh, sorry. Yeah. Oh.
I didn't got anyone's. So, what is the limitation in discounted reward? Is there any limitation first of all?
And we have to decide what gamma is. So
Yes, one of the limitation
getting
is
to the optimal value of gamma, that would be difficult.
Ma'am,
yes,
can gamma be trained?
yes.
Can it be, can we get gamma by, can it be a learning parameter? That's what I'm asking.
Okay, you are saying hyperparameter,
Yeah,
or
yes. Yes,
it can be. Then yes, it can be, but think then you are enforcing something
yes,
like
ma'am.
it's not actually happening. The problem is not actually converging. You are making the gamma as a hyperparameter and enforcing something. Are you getting my point?
Yes, so I have to do plenty of experiments, then I have to come to a conclusion about the value of gamma.
Uh,
For which gamma I am getting optimal results, something like that.
Yes, yes. But by taking the gamma as like some hyperparameter, we can say that it is something like enforcing something. It's not happening naturally. By
Okay,
taking this value, we are enforcing them to converge here.
got it, ma'am.
Actually, that shouldn't be the case here. Okay, any other limitation?
Can't we change it like a weight? Like when we change the probability, we change gamma also.
Yes, yes, yes.
But in that case, we would not going to have any kind of cost function or loss function to train the gamma against. I mean, we have to take the partial derivative of gamma on which
We
what
have
respect.
Don't confuse it with ML first thing. Now tell.
Yeah,
Madam, here the reason behind we chose gamma is one is to make the cumulative converge, and the other thing is assumption of a final terminal state. At some point, the it has to terminate. That
Yes.
the sequence of steps, that assumption. If it doesn't terminate, then there is a we are forcing to terminate. Yeah.
Yes, we are using gamma so that it can terminate, and moreover, the near-sighted rewards, like if we want to give the importance to near-sighted or far-sighted, that can be like there the gamma can be used as a hyperparameter, as one of the students said. Any doubts?
No, ma'am.
Okay, let's proceed. In map class only, I like started this thing. Then everyone was getting confused. Then I said that okay, I'll come to this thing later. You remember these two equations which I am writing.
yes, ma'am.
Yes, ma'am.
Now you got the clarity about this, or
Yes, ma'am. Kind of. Yeah.
okay? Now can you explain me if you got the clarity? What is GT first of all? What is expectation? What is condition?
Okay.
If
So
now what is the main motive? We are saying what is the difference between q pi and v pi? Yes, let's.
Yeah, so in QPy, we are fixing the initial state and also the action. But in VPy, we are only fixing the initial state.
Yes.
And we can choose the action according to our policy pi. And so GT is the expected return. And so, I mean, we will be going through the, I mean, going according to the policy pi, and we will pick a particular arm, and that will, transcend us to a new state. So from there, we also going to, and the parameters of the policy pi that will get changed, and according to that, then we will again pick another arm that will eventually bring us to another state. And then we are going to take an average of the returns. So that is what VPy.
Madam, VPy is more about the value of the state, irrespective of the action. So all the actions, we are averaging it out as per the pi. Whereas QPy is the value of taking an action in a particular state. So that means looking ahead or taking one action and then evaluating it. Whereas VPy is evaluating that state itself by taking expected of all the actions we take from that state and following pi.
Yes, the basic difference between VPy and QPy is we are at a particular state at the time S, then what is the expected return? QPy is we are at the state S at the time T, and we had taken the action A, then what is the expected return as told by both of you? So what is this? I am at S, I take the action A, I go to S dash, then take A dash. Here reward R is there, and here reward R dash is there. Now someone can tell me like from where VPy will proceed and from where QPy will proceed.
Ma'am, if we take some other action at S, so that will also be considered in VPy.
Yes.
Like the reward of that would also be considered. And what will happen in VPy is we'll take the probability of taking this action given in this state, and then we'll multiply it by the expected reward we will be getting after taking that action. But in QPy, we will only consider the action A, not A double dash.
Yes, you are correct. We are only, this is basically given to us. Can I say that?
Yeah, the first action is fixed for QPy.
Yes, but here, like for the VPy, we are only given with the state. We don't know which action can be performed from the first movement only, from the first state S itself. I think I explained you this, but at that time, there was lot of confusion. You got now?
Yes, ma'am, got it.
Coming to Markov assumption. What is Markov assumption? Before writing anything, can someone explain me?
Yes, so
Markov assumption is that the probability of going to a state of getting a reward and going to the next state from the current state after taking an action A, like it won't depend on the previous states that we have come from.
So it depends on
only the current state and the action.
Yes. We can say that it doesn't depend on the whole history. It depends on if I'm talking about the current state, it depends upon only the previous state. If I'm talking about the future state, as you told, that it depends on the current state itself. So we'll not depend on the whole history here. That is what is a Markov first order assumption.
That is first order Markov, no?
Yes.
What you just said was a first order Markov. You could have the second order Markov when we depend on two previous states.
Yes. Basically, we call Markov assumption, like we usually take this first order only. And I'm calling it as first order because it is depending on only the one last state only. You are correct that if it depends on the last two states, then we can say that. Is this equation clear?
Yes, ma'am.
Let's move forward. That history doesn't matter. Only the current state and current action matter. This is the main thing. Coming to NPTEL. An example gave by professor only. Today, I'll give some homework problems as well. In Slack only, in the class only, I'll write that. The MDP problems, which I'll expect you to solve like numerically only, like in notebook and pen, not like coding part. I'll give you one today and 2, 3 tomorrow as well.
Now, if possible, can you reshare the link to Slack group?
Okay.
Yeah, I'm doing it. Yeah.
I think only like 30 participants are there in the Slack.
Yes, ma'am. I will share it here.
Yes. So our example is that Robert goes around the building and find all the empty cans. And push it to trash. Recovery system. For every can, what gathers? Reward is equal to 1. And what is having limited amount of battery? So basically, if it goes out of battery, either it will recharge itself or will sit in a place and expect people to throw. You want these notes which I am writing? Yes. Am I audible?
Yes, ma'am.
So you want these notes which I am writing here?
Ma'am, actually,
Or no
I'll
need?
take the notes as we go along. But I wanted to ask, ma'am, that pack document that you were showing. After this, you told us to do the examples. Can you reshare that or tell us where that was?
Okay. I'll share in the Slack itself. It is Foundations of Machine Learning, the book.
Okay, ma'am.
I'll share. Okay. Yes, I'll share the notes as well, sure. So can someone explain me the problem first? What is the problem? Then we'll formulate the MDP and what is the aim here? I haven't written.
So the problem is that the robot has to, the aim of the robot is to gather as many cans as possible because it will get a reward 1 when it gathers the cans. And it has to decide whether it has to collect the cans actively or sit in a place and expect people to throw, because that will, going around and collecting the cans will drain its battery. And it will also have to decide whether to just sit there or to actually go and recharge. So because it does not know how much battery it has, so it can get switched off.
Yes, you are correct that a robot has to basically go and collect the empty cans here. And if it gather a can here, then it will get the reward 1. And if it basically sits in a place and expects the people to throw, then it's not -3, huh? Or it can sit in a place and expect the people to throw, or like it can go for recharge if it go out of battery basically. So now we are having the rewards as well. So reward basically collecting the can is 1 plus 1. If it runs out of battery, it is -3, and the recharge is basically 0 here. So what are the states here?
Battery level. I mean, it can be continuous and it can also be discrete. So it can be battery level low or high. It's a discrete state, and we can also even have continuous state. So where, I mean, 1%, 2%, 3%, every percentage would be a state in that
Why
case.
we are not having the continuous states here?
Mm,
In MDP, why we are not having continuous? Yes.
Can
Ma'am,
you
then
repeat the
you
question?
have many, the complexity of the model will increase because of so many states, and the number of parameters will also
Is it
increase.
possible?
No, no, ma'am.
Yes. So let's go with the discrete states as well. What are the actions here?
Picking the trash can. I mean, finding first, roaming around to find the trash can, and the second one that someone can put the trash can on it.
I can say finding the cans, waiting so
Yes,
that someone can place the cans.
yes.
Any other action?
Ma'am, recharging the charging.
Hmm.
Yeah.
Next time, we'll come with some other examples. This is the example which is already discussed. Next time, I'll write the question. I'll expect the answers from you of that question. The whole numerical question also.
Ma'am, you actually gave an example before.
That one also I gave, that battery and all. That was also battery, energy, draining, time and all.
Yes,
But
ma'am.
I now give the whole problem to solve.
Okay, ma'am.
So now how we are formulating this MDP basically here? Can someone tell me in detail? Now state, action, rewards. From which state to which state I can go?
Low to high or high to low?
How? Like, okay, I can go from high to low and low to high. Okay, let's take the two states first of all. So I'm in low. Here I'm in high. So what will happen now? Can someone help me in transition?
And we can go from high to low.
First
if
of
we are
all,
actively picking
yes.
cans.
High to low. When we can go from high to low?
When we are finding cans.
Yes, when we are finding cans, we can go high to low. Then,
We will have a plus positive one reward in that case.
okay, yes, one more thing, that we are saying that the probability of finding the cans and waiting for the cans basically. So which will be the actively seeking for the cans or finding the cans? Alpha, beta. What probability will be greater and why?
I'm in high state, alpha would be greater. In low state, beta would be greater.
What we want?
And that in high state, it actively seeks the cans because there is very like reward expectation would be high, and it can afford to seek the cans.
So what is the probability here from high to low? Basically, what
Very,
is
very low. I mean, not that much.
no, actually you were saying that why we went from
Alpha,
high,
right? Alpha.
Yeah.
why alpha? We are
Because we
saying,
have high power, so we can search for cans.
so we are searching for the cans and we go from high to low basically. Suppose with a 30% probability, we move from high to low, and 70% we are from high to high.
Yeah.
And we are still searching for the cans here, I can say. Or the second, I can say the other action is waiting for the cans. So if I'm waiting for the cans, what can can I go from high to low here? Let's
No,
take it
ma'am. It should be a self-flow, high to high.
high to high. Okay, but let us take it as an exception case that it is not doing anything. Still, it goes 10% of time high to low,
Yeah.
and it is beta basically waiting for the cans. Now, what about low? What about low? From low to high,
Is it will go to low to high by charging, and it will incur a penalty of -3i.
if I recharge. So it is we are recharging it. Other option from low to low.
Yes, ma'am. It can wait, and with high probability, and with a low probability, it will explore.
Basically, it is a very low probability that it will basically go from low to high. From low to low, suppose it is actively seeking and it goes from low to low.
So, ma'am, the phenomenon of going low to high, it's because for waiting or for searching, the battery actually get totally exhausted, and then it's recharged, and then it goes to high. And at the same time, it will also incur a penalty of -3.
-3 here. Yes, you are correct here.
Okay.
So basically, this is the whole transition from how we are making from particular state. We are taking an action. We are going. Some reward is awarded to us, and then we are going to the next state. Basically, this is just an MTP formulation here.
Okay, ma'am, got it.
Okay, let's go. Okay. Is it fine? I think many of the students were having the doubts in Slack related to Banach space, and some doubts were there. Am I correct? Okay, let's proceed.
Yeah, that was mostly clear.
Mhm. So what can I write GT as?
RT plus 1 plus
Plus gamma RT plus 2 plus gamma square RT plus 3 given ST is equal to S. Now here comes the main point. What is this? Yes.
Bellman's equation for V5.
What is this actually? What I have written? Can you explain how I came from this previous step to this step?
Ma'am, I'm
Ma'am, what
taking.
we did was,
Hmm?
ma'am, in this step, we took gamma as common after RT plus 1, and then we were left with RT plus 2 plus gamma RT plus 3. And that was the V5 for the next state. Like
Yes.
after we reach that,
Absolutely
so that
correct.
would be the expected. Yes.
Any doubts? I'll explain it again.
Ma'am, so this is basically the recursion part, right?
This is basically, yes. What is this? RT plus 1 is written same. Gamma, let us take here, common here. Now what we are left, RT plus 2 plus gamma RT plus 3 plus, basically I can write this. I'll write it again. Gamma RT plus 2 plus gamma RT plus 3 plus gamma square RT plus 4. It is same as this. Just we are taking another state, the S dash, the other state. So we can say that it is V pi of S dash. Am I correct?
Yes, ma'am.
Sure, I can move forward.
Yes, ma'am.
Now, wait a second, I'll have water. 1 minute. I'll write it and then I'll explain in detail. Now, can someone explain me? Then I'll explain. Like, first, I want the inputs from you. Yes, come on.
So you are summing over. So you go from a state S to S prime with an action A. So you sum over all the states S prime, which action A takes you to. Then you sum over all the actions which you take from S, and you multiply. Basically, you are multiplying the expected value of that term in the brackets. So you're summing over all actions you can take from S and also all states which you reach from S. And then
Yes.
you're creating that recursion over S prime.
One more question. Why this X? Why, if we are writing this V pi, we are not taking it out expectation thing? Why it is inside only?
Because you S prime is basically there are many S primes. So you have to do an expectation over all the S primes.
Yes, yes, yes.
So we'll be doing multiple experiments, then we'll be averaging over.
Yes, yes. Basically, I can say it is partial expectation. It is not full like expectation, because this is not the only state that is why we didn't took it out of it. Now coming to this term, I can say that, like, if I'm in a state, then what action is performed? If I'm in the state S and this action is basically performed, then what is the probability I'm going to S dash? Now, I'm in the state S, given that I'm given the action A, given S dash I'm going, then what is the expected reward? Plus gamma V pi of S. Clear?
Yes, ma'am.
Yes, ma'am.
Now coming to Q pi term. Now, can someone explain me this?
Here, ma'am, we just have fixed the actioning.
We don't have to do this term. Yes.
Yes, ma'am. Everything else is same as before.
Okay, this is removed here. As you said, this is the same here. This is the same here. What is this then?
So these are all subsequent. So from S prime, what you do,
Yeah.
once you reach S prime, you have to create that recursion again.
This is, yes, you are correct that this is basically same as V pi of S only.
Yes, ma'am.
Huh.
After the selection of array, then the system will be stochastic. It will
Yes,
act like before.
yes. Rows will sum to one. It is a stochastic basically. It is the
One
Bellman.
doubt, ma'am. Below the summation, why do we have A dash but not A?
That because this A is general term, right? I mean,
But like, why A dash for general term? A would be right.
A is the action you took when you were in state S, and now
So,
you're
so A
summing
dash is
over
general action, right? Any
all
action.
all the actions you'll take on the state S prime. So A prime is just a summation, or you're summing over any action A prime which you take at S prime.
yeah, I didn't got it. Which point you are? I mean, can you point out that particular A here? Which A you are talking about?
This say na?
Alright, it's clear.
Which one?
Which one you are asking?
Yeah, that only that you want. I was thinking why A prime we have used. But okay. That is just all the actions we can take.
Oh, okay, got it.
Can someone answer? I'm also checking by the way. If I'm in a particular state, action A is taken, then what is the probability I'm going to S dash? Then S is taken, A is taken, S dash is there, then what is the expected reward? Plus gamma, then
Ma'am,
sum.
doubt was only in syntax. I got the concept. The notation of why
So
only a
the
concept.
summation pi of A over S prime should be A prime over S prime, no?
A prime. Now, if I'm in S prime, this is just that I'm taking A prime because I'm in the S prime. I'm saying that. Just
Yeah.
that. Huh.
Okay, ma'am, got it.
Should we proceed?
Yes.
This Bellman equations are clear. Then only like we can proceed, because then these equations will be used in the next subsequent things. Is it clear?
Yes, ma'am.
ma'am.
Coming to optimal value functions. Can someone explain me this?
You're finding the best policy for which you maximize the expected returns, given you start at state S. And I guess you're doing it for all S.
Yes. I want a pi such that I can say no other pi gets, can I get the better return than this pi? It is best over all the pi's. I'll get the best policy if I'm in the state S, and the maximum return should be the the expected return should be the maximum one. Is it clear? What is this
Yes,
term?
ma'am.
Yes, ma'am.
What is this term? Expected GT given ST is equal to S.
V finals.
The returns given the state. Like B, okay.
If the state is given, we have to find the expected return, that is basically value function as we discussed here. And we are basically finding the optimal policy pi star here. Wait a second. What is argmax and max? Last difference. What this equation tell us?
Ma'am, for which particular set of parameters of the policy function we are getting the maximum expected reward
What is
return?
argmax?
So what is the pi which maximizes V
Yeah.
pi?
Indexing basically. basically, what is the term like which maximizes V pi as you told? Is there an optimal policy?
There could be many optimal policies.
There can be many optimal policy. There is basically not the optimal policy or unique optimal policy. As a great example is shared here.
Before that, I have one question.
Yes, yes.
In like we are considering different policies. So if we're taking discounted returns, then in each policy will the value of gamma be same or different?
What can you
Yeah,
repeat?
when we are taking the we want to find the best policy. So for each policy, the value of gamma will be same or different.
We'll
Same.
take a same gamma, na?
Yeah.
We are fixing a gamma. We are not saying that gamma will change in a problem.
And ma'am, I have also one question. So the pi will change according to the update rule, right?
Yes, yes.
Okay. Okay.
Any doubts? Should I proceed?
Ma'am, I had that earlier question that I asked you in the start of the class about
Yes.
what will
Yes.
be an MDP with stochastic rewards.
DP with stochastic rewards. With changing rewards. Can rewards be stochastic?
Ma'am, rewards are stochastic, right?
Okay. So you're saying rewards are changing basically. Yes, rewards are changing. Why rewards are stochastic? Let's come to the solution.
Because they are in a distribution, so every time it will be different.
In the bandit arm context, every time you pulled the arm, you got a reward, random reward pulled from the distribution. So
Yes, 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 yes.
Ma'am,
Now-
even for in our this particular case also the pi function is basically the policy is just basically giving a probability distribution, right?
That is obviously stochastic here.
Yeah.
Now what is the question? So I again forgot. Yes, Ashley.
Yes, ma'am. So I was wondering whether, is there any difference between deterministic rewards and MDP? Like, how can that be? That was
How-
what was that?
How can
So,
the rewards be deterministic, you are saying?
yes, ma'am.
It depends on problem to problem. If suppose I'm taking a very simple problem where the rewards are like deterministic only, I am saying, okay, I'll take I'll give you the problem in Slack only, the example in the Slack only, like the problems where we are having deterministic as well.
So, ma'am, examples we have discussing so far in MDP, they all have stochastic rewards, right?
Yes, 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 yes.
Okay, ma'am. So, ma'am, okay, ma'am. So that was a week 4 question. So I don't think we can discuss that here, right?
Yes, yes.
So ma'am, in the case of deterministic problems, I think there would not be any kind of probability distribution, right?
in the case of the problem you discussed about, that's a deterministic reward. No, that's not a stochastic reward. Every time you pick a can, you get +1, not any other number.
Yes. We have probability here, and the rewards are not stochastic as well. Yes, you are correct.
So the only thing is, you get a reward with a probability alpha, I guess. So that is the stochasticity, is it?
Yes.
The reward value is fixed, but the probability of getting the reward, that is
Okay.
So true reward is fixed, like which is 1.
What I am having question, can the rewards also be stochastic now?
yes, ma'am. That is the case we're dealing with right
Yeah,
now.
if we consider that the robot can pick multiple cans and each can has 1 reward, so it might get multiple cans at once. So like
What
if we
should be the reward then?
So this looks like a simple Bernoulli distribution where you get +1 with probability alpha.
If you don't pick, then beta basically. If you are no, that is basically battery recharge.
It is alpha and 1 minus alpha, right?
One
Yeah.
minus. Okay, we'll discuss that in more detail. Yes, yes.
If we consider that, like we have only taken low and high, if we take one very low also, and then we actively find, then it is almost sure that we will run out of battery. So can we say that is deterministic? Because in that case, every time we will get -3.
What is the example you are saying? We are having low, high, and very high.
No, very low, very low. Like
Okay. Very low means you are always like going out of the battery, and you always have to go to the
yeah,
recharge.
if we actively search.
Then we are saying that it is deterministic case only.
Ma'am, then it is depending on the problem formulation, right? How we are formulating the problem.
That is what I am saying, that I'll give you the problem examples, that where the problems are basically deterministic and where they are probabilistic here.
Yeah, got it.
Okay, there is a question. Madam, I'm confused with pi and q pi. Can you explain with example? You may send me a mail if possible. Okay. Also, I joined today. I have a link. Can I have a link for recorded lecture? Okay. It's a direct message. Sorry. Okay, I will share afterwards. Okay, let's go. So where were we? That we can have many optimal policies as well here. Now, is this unique or not? The value function.
Yeah, the value function has to be unique.
Value function is unique.
Yes.
So we can attain the maximum return, expected return for multiple policy, right? Okay.
But the value which we'll get, that will be unique here.
Yeah. So the maximum value that we are gaining, that would be fixed, but that value is achievable for different sets of policies.
Actions, I can say state action pair policy.
Yes, ma'am.
Is this correct? First of all, what is this and is this correct equation?
Yeah, it seems correct because we are first taking probability of reaching in a state given a state with a previous state interaction, and then we are taking expected like rewards that we can get going from one state to another using an action, and then the gamma part is all the future rewards.
Okay. Now I'll write another one. Which one is looking more okay? What is the difference between two equations?
They're same.
Ma'am, in the first equation, we have fixed the action. So in the first, we didn't consider that optimal S dash, ma'am. Have you accidentally missed that adding that max in Q star essay in the first one?
Max is here. That is what I'm asking. This is the difference. Max is here. Here the max is here.
Yes, ma'am.
What is which one is more?
In the first one, we are taking optimal action from the first step, and in second one, we are taking.
Max here?
What?
Do we require max here?
No, it is not dependent on pi. Those terms are not dependent on pi. So you can, that's why you could bring that max pi inside on v pi.
Doesn't matter.
Yeah.
Like,
Anyway, in the first state where we are going to pick action A. So whatever may be the policy, we don't care.
because it's Q basically, so it's not value function. So first action is A anyway. It is not dependent on the policy here. Then
Yeah.
after going to S dash, then what is the reward? And then what is the, after that we'll say that what would be the max of pi. First say, is first say optimal?
No, not necessarily.
It can be.
It can be, it cannot be, not necessary. What about value function?
Yeah, value
Yes,
function, I
yes.
think you'll always have an optimal action.
Yes, you are correct. What is this? Can someone explain me? Is this correct?
Yes, ma'am, it is correct. Ma'am, it means that at every state we are considering only that Q star, which only that action which has the maximum Q star on that state. So that is basically the value function.
No, you choose the first best action, first action.
Yes. You got it? Yes, Ashi?
Yes, ma'am.
Can you tell me?
Ma'am, basically, what we are doing is.
And first thing, what is the difference between B and Q?
Ma'am, Q means we have fixed an action.
First action is fixed.
Yes, ma'am, first action. Yes. So we are selecting that first action for which the reward is maximized.
Yes.
In that state.
Any doubts with this equation? We are saying that our first action is also the maximum one. Then can I say that Q star will be equal to the V star?
Yes.
Yes. Writing the same equation, just which I wrote before. Is this fine?
Yes.
Just we are taking the V star here, and we are saying that the max, the first action is the which is giving us the max of that. And can I say that this is the Bellman optimality equation for basically V star here? I think someone was asking me in the last class about. I think Bihan, you were asking me about in the last class some doubt about the next lecture when I told you that I haven't done that. Like, I think this first one only long term returns only.
Yes, ma'am. I was confused about that particular stochasticity nature of picking the action A. I was assuming the action with highest probability will always be picked up.
Okay, now it's clear.
Yes,
Every
ma'am.
okay. Now, can someone explain me what is this 5 star here?
Optimal policy.
And what this equation is telling us?
So at state S, what is the optimal policy to pick? What optimal action to pick?
Yes. So basically, what is the optimal action we have to pick? That is only what the policy tells us when we are at the state S. And this is basically, I can say that 5 star of S is R max. It's same as 2 star. Is this both like both of the equations clear? Or I'll go in more detail. Yes.
Ma'am, I wanted to ask some doubt related to this only.
Yes.
So here we have written deterministic policy, right? So, ma'am, for all MDPs, will there always be a deterministic optimal policy? Like, is there a case where it won't be?
No, wait a second. I'm basically signed out. Yes, we'll not always have the deterministic policy. Am I audible?
Yes, ma'am. Ma'am, did you say we may not have a deterministic policy?
We may not have deterministic policy, yes.
Okay, and ma'am, can you give an example for that?
Yes, yes. Wait a second. Actually, I'm logged out of my laptop. 1 minute.
But
Ma'am,
here we are not yet in the reinforcement learning setup. No, we are in just in the MDP setup. So
Oh,
that
you're
is
not
for
doing MDP as RL?
I think it's in full RL, right?
so explore exploit will happen when you are in the RL setup. No, here we are still discussing MDP, Markov and decision process.
So, what do you think? MDP is a part of RL or no?
I think RL is a way to do MDP. So since I mean, as it was mentioned in the class, that P of S prime given S and A is difficult to formulate or derive. RL is a way to figure out those P's.
Wait
So
a
I
second.
think
Actually, my
according
recording is stopped. 1 minute.
Ma'am, can you give a 2 minutes break?
Okay, okay. Yes,
Okay.
I also have. Let's take 5 minutes break here. 7:25 we'll proceed. Can we proceed?
Yes, ma'am.
I think we'll wait for 1 more minute, 7:25 as I told. So, how is the class going? Some clarity you are getting, Rola?
Yes, ma'am.
Yes, ma'am.
I should have written the question till that time.
Madam, just referring to the just question asked by our colleagues, generally in reinforcement learning, MDP is not given. MDP is not given. Our goal, I understand, in the RL is to discover MDP. Am I correct?
Some people take MDP as a part of RL as well. It depends on person to person. Some take it is basically model based RL as well. Model based means in which I'll go in detail further. And some people say no, it is not a part of RL. It is basically like we can use it or so. But some take it as a model based RL and as a part of RL as well.
Okay. Okay. Okay, that means we can solve RL problem without MDP also, right? So, right.
Yes.
I think it is more the other way around. You could solve MDP by brute force, or you could use an RL approach to solve MDP. MDP is just a formulation.
Okay, but can I say that value iteration and all they are used in MDP and all? Okay, that is what you are saying, that RL problem can be used to solve MDP. Am I correct?
I'm just so based on the class, I don't know anything further than that. But in the class, it was mentioned that he had given an example of the sheep or cows he had given, and he's told us how difficult it was for them to set up the P, S prime, and S comma A. And RL essentially removes the need of setting up that P, S prime given S comma A. So that led me to the conclusion that RL is one way to solve MDP or coming up with optimal policies.
I can say Markov decision process. Still, there is a according to me, it is a part of RL. Yes, we can come up with value iteration, policy iteration to solve this MDP, like a mark of this formulation, I can say. In that perspective, you are correct that RL techniques can be used to solve this MDP.
Madam, when you say solve MDP, means MDP is given and find out the value function, right?
It's just MDP is not, I'm saying formulation is given, a problem is given. MDP formulation in the sense, state is like, everything will not be served. We have to find what is the state, what is the action, what is the reward. If the transition probabilities are given, then only the MDP can be applied. Then how to proceed forward, then value iteration or some other techniques are applied here. Okay, we'll go in the next class, we'll study about this, and then I'll give the question in the Slack as well. Then we'll try to, that is also solving the MDP problem only.
No, I'm getting confused. MDP means transition probabilities.
No, MDP doesn't mean. MDP means Markov decision process. What decision you should take if you are in a particular state. What is the best policy? That is whole MDP only.
Yeah. Okay. MDP means if you are in a current state, if you take an action, which state you get into, that is an MDP.
Yes.
So, ma'am, what happens? So, in cases where the number of parameters that is influencing our decision of taking an action A, so if that tremendously increases, then in those kind of cases, we can't actually formulate the Markov decision processes by ourselves, right? As the complexity of the model and the number of parameters increases, it would.
Yes, because it will be very computationally complex. If I have so many states, then it will be difficult for me to maintain such a large table Or I can say if I'm in this particular state, this random factor is there, then what action I have to perform. Then if I'm in this particular state, some other random factor is there. And if I'm having large number of states, that like if randomness is so much, then also it is difficult for me to like go for MDP approach. If I can say large number of states are there, then also it is difficult. So there are limitations which will come along the line.
Okay, so ma'am, is it the point of inception of deep RL? I mean, from this ground, are we moving towards the deep RL to handle so much, high number of parameters and randomness that influences the decision making?
Yes, that is the direction. Now we'll go to deep RL, then model free approaches. It is basically called model based. I'll tell you afterwards only after the
Okay.
coming classes. Otherwise, some confusion will be there. Okay, now where were we? So let's say what is a Bellman equation? Same equation I have written. Optimality equation.
Ma'am, do we have deep RL in our course?
No, I don't think so. We are having that.
Okay.
This is more inclined towards the theory part here.
I see. Yeah.
Like if you want to go to research industry, then
Yeah.
these concepts will be very useful. Some like maths and all.
Okay, ma'am. Got it.
That deep RL, it's mostly coding part. You also know.
Yes, ma'am.
This is the basic insights and all behind that.
Okay, ma'am. Got it. Ma'am, will it be possible for you in future to extend the session to, give us basic intuition about deep RL?
Okay, I'll try that. Okay.
Okay, ma'am. Yeah, that would be great.
So you all got these two equations. First of all, I want to ask, then I'll proceed forward.
Yes, ma'am.
If I'm saying that instead of this, I'm using this, what do I mean?
That is deterministic, madam, pi of s. This is a stochastic policy, left one.
Why?
Because what action to take is random.
Yes. Now here pi of s means what? Whenever I'm in the s, then I'll take this action only.
Yes, that is deterministic. Yeah.
That is deterministic. Now,
So you will be giving an example of MDP where we have where we don't have an deterministic policy in Slack itself.
I have given the last, okay, I'll give this in the Slack itself. If I'm not having the deterministic policy, suppose I gave the example last time also that we are having a battery, suppose this is, okay, let's take an IoT device. This was example given, IoT device. This is basically a server. I want to transmit basically the data here. I don't want my battery should be exhausted that much, and with some transmission power I'm transmitting it, and the other hand I want it should be transmitted quickly, the time should be lesser consumed here. So I have to like take an optimal action transmission power, whereas the bandwidth is changing. This is the randomness. So whenever the randomness is there, if I'm in this particular state, because of this randomness, my action will be influenced. Maybe
Yes,
I'm in the S state and this action I'm performing because of this bandwidth 1. But suppose the bandwidth is so much that I'm performing, or very low that I'm performing some other action in this same state. Now, can you say that we'll have the deterministic policy?
so ma'am, the policy would be our probability distribution over the actions, or will it be a function of bandwidth?
Now you're saying that yes, it is a function of bandwidth here, it is a function of randomness there, but then also we are saying that it is deterministic. Is it deterministic first of all? What do you think?
No, with some probability you are taking in the state S, you are taking either A or A prime.
So I'm in the same state, either I'm taking A or either I'm taking A1. Okay,
Yes,
I'll give.
ma'am, now I got it.
Got it, na? If you want, I'll give you some other example as well in this Slack.
Thank you, ma'am.
So talking about the norms. Okay, first of all, let's first talk about value function as a vector, suppose which has S states, and we are assuming that we are having finite MDP where S and A are finite here. With S components, I can say V pi, I can say with S components here. What is max norm? I think this question was asked in Slack itself. I checked it late when the answer was given.
It's the Euclidean norm, yeah.
Is it Euclidean?
No, just pick the element which has the maximum value.
Maximum.
Euclidean is the other one. This is the infinity.
Yes.
Or what is this term?
Super num.
Yes.
This is super num. This is the same max num notation.
Supremum. So what is supremum?
The norm which we take maximum value.
Least upper bound. I think someone gave a very good example in Slack itself. What do you mean by least upper bound?
Like the minimum value which is greater than everything in the set.
Yes. Is it clear? Should I proceed?
One thing, can you tell why is V prime has S components?
What is S?
States.
So how many components we are saying that how many components it will have if we are having S states?
Okay, all the states. Okay.
All the state, the number of the states will have that much only we'll have the V pi. Na? Can I say for every S I have to calculate the V pi?
For every unique S.
Yes. So is it the magnitude S components?
Yes, yeah. If we have for every unique S, then we can.
Should I proceed? So basically, norm has some properties that it should be non-negative. It is 0 if x is 0 basically. If and only if, I should write. Homogeneity property. This is just the property of the norms here. And the triangle inequality. These are just the properties I'm mentioning that will be used further. Basically, triangle inequality I think is used.
One thing, how can we apply supremum on S? Like S, can it be quantified? Like, okay, value of S.
Value of S basically, yes. That is what I was thinking. Why S? Should I proceed?
Yes, ma'am.
Now coming to complete normed vector space. Before that, coming to Cauchy sequence. Can someone tell me what is Cauchy sequence? We mentioned in the starting of the lecture itself.
Yeah, so after some iteration, like some point n, the difference between any two elements will be less than some value epsilon.
Yes, you're absolutely correct. After some point in the sequence, like if I'll pick two elements, then I can say they are within epsilon of each other. Is this statement correct?
Yeah, for any epsilon.
For any real epsilon, I can say. Can I say this? Wait a second, let me write. Sequence in which elements are coming closer and closer to each other. Is the statement correct?
So depends on the norm which you're using, I guess. So is it with respect to the max norm or any norm?
Cauchy sequences with respect. Now I'm not talking about the norms here. What I'm saying is, suppose I'm taking a sequence. After some point, they are coming closer and closer to each other. That is basically the Cauchy sequence. Suppose if I take an example of 1 by n here. Can I say
Okay,
that?
so it's a scalar, not a vector. Each element is a scalar, you're saying.
If I suppose that it is a scalar, then can I say 1 by n is a Cauchy sequence?
Yeah,
Yes.
Why it is Cauchy sequence?
because the difference gets smaller with I guess time.
Yes.
Yeah.
Yes. So after some point, it is coming closer and like the sequence is coming closer and closer. And after some point, the difference will be less than the epsilon part, I can say.
So in this case, if like V is the our Cauchy sequence, then the value of Vs will come closer and closer.
Yes, we'll come to that value function Cauchy sequence. We'll come to that proof also. Don't worry. So can you give me the example? Okay, I gave that this is the Cauchy sequence. Can you give me some example which is non-Cauchy sequence?
H
N.
square, n square.
Yes, n square simple. It is not Cauchy sequence. Now, what is this complete space basically? What do you mean by complete space? Or Banach space, I can say. Complete normed vector space, Banach space. What do you mean by that?
The convergence point will be in the set itself.
Convergence point is in the space itself, that set itself. Yes, you are totally correct. That basically we are having, first condition is that we are having a Cauchy sequence that is converging to the limit that is also itself in the space itself. I can say Cauchy sequence converges to a limit that is also in the space. Can someone write in the, like all of you, can you write for like complete space examples here? Okay, can you tell me a Cauchy sequence which is not complete space? Yes, behind, for a function to be Cauchy sequence, it is mandatory for it to make horizontal asymptote, right? Can you explain me your statement itself?
Ma'am, for the gap between two consecutive numbers or the values to get smaller and smaller, it has to make a asymptote. Otherwise, it would not happen. I mean, graphically, if you take a look at it.
Can you repeat? If a number, can you repeat your statement?
Yes, ma'am. So for suppose we are having a function and then we're trying to determine whether it is a Cauchy sequence or not. So for
Okay.
it to be Cauchy sequence, if we plot the function, then the function must give a horizontal asymptote. So that's the only condition where we can see this kind of phenomenon where two immediate values, the difference between them will keep decreasing as we move forward or
Yes,
as
yes,
input
yes,
increases.
yes, you are correct.
Okay, ma'am. Yeah.
Now, can you give the example? Ma'am, in the lecture, professor said convergence point may not lie in the vector space.
1 over n is not complete, no?
1 over n is not complete. Why?
Because 0 doesn't lie in the sequence.
Okay, let's take n starting from 1. Okay, Ashi, can you tell me that what you are saying, convergence point may not lie in the vector? Can you tell me?
Ma'am, am I audible?
Yes, yes, you're audible.
Actually, I tried speaking earlier. Maybe I was not audible then. Ma'am, in the lecture, professor talked about this thing that, ma'am, although Cauchy sequence converges to a limit, that limit may not lie within the vector space. I think that
Yes,
was
yes,
the case.
yeah, yes, that is true. Cauchy sequence may not lie in the vector space. That is basically not a complete space. That is not a Banach space. That is what
Yes,
I'm asking.
ma'am.
Is there an example which you can say that this is a Cauchy sequence and it doesn't lie? It is not a Banach space, which means that it doesn't lie in the same space itself. All Cauchy sequence are not Banach space. Now, can I say the reverse? All Banach space or all complete sequence are Cauchy sequence?
Yes, ma'am.
Now, what is this a Cauchy sequence? First question.
No, ma'am. It's e to the power x. No, I don't.
Okay, leave this. Is it a Cauchy sequence?
Uh, no, ma'am.
Why?
That because it's not decreasing the
Yeah,
gap.
no, it will decrease. It's
It's an
three.
increasing function. If
It's
we take a
2
look
by
at it.
4, 2 by 4 by 2. Then there's 27 by. No, I think x, if it takes square continuously, then it will be.
Ma'am, I think it is a Cauchy sequence because after a certain point, it does start getting closer and closer.
Yes.
Can we
After
also take n minus 1 by n? That will be, I think,
I'm not
Banach
getting.
space.
Might have been.
okay, we'll come to this example.
So it depends on x, no? I guess x is, if x is between 0 and 1, then it is a Cauchy sequence. If the x is greater than 1, then it is not a Cauchy sequence.
Yeah.
If x is greater than 1,
Then it would not be, ma'am, I think.
1. Okay, let us take 2 basically. Then
I think even then it would be Cauchy sequence because
Yes.
if we make the n large enough, the elements would start coming closer.
yes,
Because my factorial would increase
yeah.
more than the x.
Yes, ma'am. Yeah, I was getting it wrong.
Factorial will
Absolutely
increase.
correct. Yeah.
Now the next question is it a Banach space?
Ma'am, what is a Banach space? I actually haven't gone through the video yet.
Banach space is complete space itself. Okay, I'll come after this example. Maybe you will get it more clearly.
Okay, ma'am.
That Cauchy sequence is converging to a limit that also itself is in the same space. I'll give this example.
Again, it will converge to 0, right?
It is basically e raised to power x if we'll go to the Taylor series. This is the formula of the Taylor series, which is equal to e raised to power x. It is converging to this. So is it a Banach space? Read the definition again. Complete space or Banach space. Cauchy sequence converges to a limit that also is in the same space.
Ma'am, finally x to the power n upon n factorial would converge to 0. And we do
I'm
not have
saying
0.
that, according to Taylor series, it is equal to e raised to power x, converging to e raised to power x.
But that is sum of the sequence.
Sum of the sequence, basically, not converging.
So we have to take convergence, right? Not sum.
Okay, let us take it as a homework problem. Think about this. That is it a Banach space or not? Take a photo or something. In the next lecture, I'll ask.
Ma'am, I think this might be the Banach space because
Okay, let's take it as homework and write in the Slack. I'll expect this time. Pack examples I'll write now only in the Slack only.
so the book name was Fundamentals of Machine Learning, right? For the pack optimality examples.
Yes. Foundations of machine learning.
Foundations of machine learning. Okay.
Madam, for details of Cauchy sequence and the Banach space, which book or any reference for?
Actually, it's basically function analysis. The more of I can say mathematical part. So we don't have to go that much in detail to get the RL thing. Just an overview we have to get. That Cauchy sequence is nothing. The Cauchy sequence is when after some point the sequence is coming, the elements, the consecutive elements are coming closer and closer to each other. That is Cauchy sequence. Then they are converging to a limit that is basically a point that is also in the vector space, in the same space, in the same vector space, that is basically Banach space. We'll give get some examples in the Slack only. I'll suggest you write some examples. I'll write now only pack learning examples.
Okay.
Is the message delivered? Can you see in the Slack?
Yes.
So let's move forward. I thought we'll complete this contraction thing also. Okay, in this, I think someone was having doubt. We'll clear this in this lecture only. Shouldn't be delayed. I think Shaurya was having doubt. Am I correct?
Is this from last class? In this lecture, I don't have. In this week, I have no doubt.
I think you have posted in the Slack itself some screenshot, which is the noun link. Okay, I'll go then I'll tell you which screenshot. Okay. First of all, what is this?
Madam, is it a reward over pi?
Yes. What? Yes.
Yeah, this first time I'm seeing this kind of equation. Just explain me, sir.
Okay, can someone explain? Then I'll explain.
Yeah, it is a reward. You can get expected reward at state S.
Can you explain this whole term, like how we are getting that?
I mean, the reward also is stochastic.
So you could
So I'm in
After-
the
you could
S.
go. You could take any action at state S, and for, any that action could take you with some probability to any state S prime. And
Then
what is the your expected reward given S A and S prime is that E term, expected term.
Correct. So we are at a particular state, then what is the action there? Then if we are given with the state as well as action with some probability, the same equation I have written, just not with B pi, I can say. Then what is the probability I'll go to S dash? If I'm the state and a particular action is performed and I'm going to S dash, then what is the expected reward there?
Madam, here we have removed the long term. It's all short term, right? Reward is a short term.
Can someone ask? Yes.
Yeah, this is one step.
Yeah, immediate reward.
Yes, it is one step. If you add long term, it becomes V pi. Yeah.
So you are correct here. It is one step transition.
No, this was my doubt. I
Yes,
just wanted
because
to
of
know
our-
how it is S-dimensional. That I understood before.
Okay.
Ma'am,
I'll
this
come
is
and come to
first,
your doubt.
the first step transition. This is because of our assumption of MTP, right? We are ignoring all the other states, the past states.
No, that is
No, this is future. No, future you are ignoring.
Yeah, so the future is depending only on my current state. The only reason that because I have
that is something that is MDP. That is there. Sorry, that is first Markovian assumption. That is there.
Yeah.
That depending on the last step. Now first step like one step. I don't have to write first step. One step transition means that only the next state we are saying. We are not saying of the future. Basically,
yeah.
whole future.
Got it, ma'am. Got it. Yeah, sorry. Yeah, got it.
What is this? What is
So probability of going to state J from S,
yes,
given
so,
all the actions.
so what is the probability that I'll go from S to A first of all, and then if I am having the state as well as action, then what is the probability I'll go to the J
For all actions.
for all actions. So if I'm using the deterministic one, now I think this was posted by you, Shaurya. The next equation which I'm going to write. Then I wrote it that we'll discuss in class.
Yes, ma'am. My doubt was only about the size of R. Like, why is it S dimensional?
I
Yeah.
think, but you, this equation. Okay. Your doubt was why it is S dimension. Okay.
Yeah, that we covered with B.
But these two equations you are not getting.
No.
Okay, now I'm saying that I'm using the deterministic one. Then then what? The same thing we are using pi of s here. Someone can explain me why we are using pi of s here instead of that?
Because it is deterministic, so only one action we will take in the given state, depending on the policy.
Yes, absolutely correct. The same is with this. So R pi is S-dimensional vector. I think now it is clear. Now coming to stochastic matrix. I think gate of actually I have to go somewhere, or we'll continue this class the next day. I'll just give you the gist. Like we'll have that thing like how the V pi is basically for like the value function is basically the Cauchy here, and then we'll discuss about the contraction mapping. Can someone tell me in short what is contraction mapping?
Yeah. So whenever we apply the operator, we are coming closer. The points will come closer.
So all those things we'll discuss and we'll continue this lecture the next time. I have to go somewhere. Otherwise, I was thinking that the proof and all of contraction mapping we'll discuss today. So, is everything clear what was discussed today? Any
Yes,
doubts
ma'am.
in this class?
Yes,
Oh, this
ma'am.
is good. Thank you.
Okay. Wait a second. I have to write the problem. Otherwise, I always forget to reply and write it. That homework problem of MDP. Okay. Wait a second. Let me write so that you can also go through it now. I'll write in the Slack itself so that everyone is in Slack now. Am I audible?
Yes, ma'am.